Hi guys, I'll be discussing the first half of the lecture. The other half I'll be covering in lecture itself, in class. So just real quick, I'm going to recap what Ben covered for transmission line theory on Tuesday. Then I'll be covering the concepts for voltage reflection coefficient, standing waves, and power flow for a lossless transmission line. So quickly, why transmission line theory? Why do we need it? When do we use it? Well, when the wavelength of the operating frequency is much shorter than the transmission line length, then you're going to have some sort of variation of the voltage and current along the transmission line. And really, transmission line theory is there to help us understand and properly design circuits and systems under such conditions. So, if we consider the traveling waves of a transmission line, their solutions are actually quite similar to the plane waves, the E&M plane waves that we considered earlier in the class. So let's take a look at the parallels between the two. If we recall how we found the plane wave solutions, we started off with Faraday's equation, where you have an electric field coupled to the magnetic field. And the same thing with Ampere's equation, where you have the magnetic field coupled to the electric field. Then we played around with those two equations, and we ended up with a plane wave equation, where we then introduced the complex reflection coefficient gamma. Then we made an assumption, a simplifying assumption, where we only had an x-directed E field component, which then allowed us to simplify that wave equation down to a second order ordinary differential equation. And we defined gamma, or complex propagation constant, as as minus omega squared mu epsilon, where it really could be a complex number consisting of a real and imaginary part. So we then said that the solution to the plane wave equation, equation number 4, consists of a forward traveling E field and a backward traveling E field. And then we finally introduced the concept of wave impedance eta, which is the ratio of the electric field over the magnetic field. So going over transmission line theory, we actually have very similar expressions. So equation number 8 gives you the relationship between the voltage and the current. Equation number 9 gives you the relationship between the derivative of the current with the voltage. And we manipulated those coupled equations to give us the wave equation, and we also have a complex propagation constant, gamma, which is now a function of resistance, inductance, conductance, and capacitance per unit length. Then we arrived at the general solution of that wave equation, which consists of a forward propagating voltage and a backward propagating voltage. And then we finally introduced the concept of characteristic impedance, which is the ratio of your incident voltage over that of your incident current. So the next concept that we have is voltage reflection coefficient. If we consider propagation along a lossless transmission line, where the transmission line is designated as this center section, and we have a generator connected to the left of that transmission line, where the generator has a voltage of V and impedance of Z, and of course that generator is located at Z equals minus L in terms of the Z axes. Then we consider a load impedance located at Z equals 0, and that load impedance is designated by ZL. So in general, that load impedance, ZL, does have a real and imaginary part. So the real part represents a resistance, and the imaginary part represents a reactance. Now we already know the general solution for the voltage and current anywhere along that transmission line as a function of Z. However, we do have to consider the boundary conditions. In this case, the boundary conditions consist of the load and our generator. So let's consider our boundary condition at z equals 0, our load. Our load essentially is the ratio of our voltage over the current, and if you plug in the expressions for the voltage and current and you evaluate at z equals 0, you end up with expression number 18. And if you solve for your reflected voltage from equation number 18, you end up with the reflected voltage being a function of your incident voltage and something that we call the voltage reflection coefficient, which is just the ratio of the difference between the load impedance and the characteristic impedance over the summation of the two. And in general, that reflection coefficient is complex, so it does consist of a magnitude and a phase term. And that complex reflection coefficient will be real if your load impedance is real and your characteristic impedance is real, which designates a lossless transmission line. And if that's the case, then you have your voltage and current in phase on that transmission line. However, let's consider the other case where your reflection coefficient is complex, and that's the case if either the load impedance is complex or the characteristic impedance of your transmission line is complex, which means you've got a lossy transmission line. And under such circumstances, your voltage and current are out of phase. You could also represent your reflection coefficient as a ratio of your reflected current over that of your incident, with a negative sign in the front. So let's take a look at, so just a real quick recap for this section here where we discuss the voltage reflection coefficient. Really, you can look at the reflection coefficient gamma as a measure of the mismatch between the load, okay, this is your load, and your transmission line here. So essentially it gives you an idea of how much your incident beam is being reflected back, or excuse me, incident voltage. Alright, so let's go to the next concept, which is standing waves. So using equation number 15 and 16, which were the general solutions right here, 15 and 16, which were the general solutions to your wave equation, we then plug in the complex reflection coefficient gamma, okay, and we arrive at two equations, 22 and 23, where they're very similar to what we've already seen before. So if you recall, for EM plane waves, where we considered the case where we had region 1 air and region 2 being some sort of media, where there was a mismatch at the interface of the wave impedances, we were able to calculate the total electric field E1 in region 1 to be the summation of an incident and a reflected field. And that took the form that you see here, and that's really analogous to equation number 2 that you see, or equation number 22 that you see here for the voltage along the transmission line. So again, what you see for equation number 22 and 23 really is just a summation of the forward and backward propagating waves, and that gives you a standing wave. And if we wanted to look at the voltage on that transmission line, we would consider the magnitude of the voltage that we have, and if we plot the magnitude of the voltage and the current as a function of z, the distance along that transmission line, where to the right of z we have the load, and to the left we have the transmission line with characteristic impedance Z0, we see that we have a variation of our voltage, okay, and a variation of the current as well, where the magnitude or the max of the current corresponds to a min of the voltage, and vice versa. The min of the current then corresponds to a max of the voltage, where the peak to peak length is half a wavelength. So as a figure of merit, as a way of describing the strength of the reflection that you have at the boundary between the load and your transmission line, we have something called the voltage standing wave ratio, or VSWR, and that's really just the ratio of the maxima of your voltage over the minima of your voltage, and that is just, of course, a function of your reflection coefficient gamma. So just a real quick recap, what are standing waves? It's just the summation of your forward propagating wave and your backward propagating wave, where you have, in some instances, destructive interference of the two, giving you a min, and constructive interference, which gives you a max. And we have a figure of merit to describe that relative or that mismatch between the load and transmission line, known as the voltage standing wave ratio. So the next concept is power on a transmission line. In this case, I'll be considering power on a lossless transmission line, where the time average power flow along the transmission line is given by equation number 27, which is half times the real part of the voltage along the line times the conjugate of the current on the line. And really, this is analogous to the power density for plane waves, which we looked at last week. So let's try to solve for the average power as a function of the reflection coefficient. So using equation number 22 and 3, which is really the general solutions of the voltage and current with the reflection coefficient, we find, let's double check that that is the case, 22 and 23, that's right. We find that the average power flowing down the transmission line, which is also the power that is dissipated in the load, is given by equation number 28, which all simplifies down to this expression down here. And if we further simplify that, we find that the average power flow, again the power that is dissipated in the load, is given by a function of your incident voltage, your characteristic impedance on the transmission line, and the reflection coefficient between the load and the transmission line. So dissecting this equation, we see that the average power flowing down the transmission line is just a function of the forward propagating wave and that of the backwards power. So let's go through a quick example where I've got a reactive load, okay, which basically means that my impedance is purely imaginary. So in general, my impedance, my load impedance, is real and imaginary, and since it's reactive, it is purely imaginary, and our resistance goes to 0. So our reactance can be either capacitive or inductive. If it's capacitive, it takes the following form for the impedance, where it's just minus j over omega c, and if it's inductive, then it takes the form of j omega l. Now, if the reactive load is purely imaginary, then the voltage and current are 90 degrees out of phase, and the average power flow becomes 0. So that implies no power dissipated in the load. And we'll take a look at why that is the case. So if we calculate the reflection coefficient and we plug in the values for the load impedance and the characteristic impedance, we see that we have a complex reflection coefficient given by some magnitude and phase. If we calculate the magnitude, we see that it evaluates to 1. Now, revisiting the expression that we had for the average power, which was found to be a function of the incident voltage and the reflection coefficient, if we plug in the value that we just found for the reflection coefficient, which was 1, then all the incident power is reflected, which implies that the average power down the transmission line, or the power dissipated in the load, is 0. So for a purely reactive load, which gives us a magnitude of 1, then we have no power dissipation. And if you consider the phase calculation which is nothing more than the arctan of the imaginary part over the real part. So going back to our expression for the complex reflection coefficient, this value here is complex. It has a real and imaginary part. If I take the imaginary part over the real and I look for the angle, that gives me the angle of my complex reflection coefficient. And if your reactance is greater than 0, that implies that your phase falls somewhere between 0 and pi, and this corresponds to an inductive case. And if your reactive part is less than 0, then you have a phase that falls between minus pi and 0, and that corresponds to a capacitive case. And that concludes this segment.